When I received the email from Professor Josh Wynn that morning, just before my routine jog at sunrise, I found myself reflecting deeply on the philosophical and methodological challenges he raised regarding our interpretations of the interstellar object 3I/Atlas. His points were precise, thoughtful, and in many ways, uncomfortably accurate. He began by acknowledging his engagement with my essay and the anomalies I had listed, expressing both interest and enjoyment in following the unfolding story. Yet, he immediately honed in on a critical weakness in my approach, which was the lack of predictive rigor. His concern was not merely pedantic. It went to the heart of how we, as scientists, assign significance to observations. He pointed out that none of the anomalies I had highlighted were anticipated in advance. From a strict scientific standpoint, this meant that the probabilities I had assigned to them were not robust. He illustrated this with an example that cut to the core of the issue: the trajectory of 3I/Atlas. It is indeed striking that the object's path is nearly anti-aligned with the ecliptic. But Professor Wynn was careful to note that it would have been equally interesting if the trajectory had instead been aligned with the ecliptic perpendicular to it, or oriented at any other arbitrary angle, including exact alignments with the Sun's equatorial plane, Pluto's orbit, Halley's comet, or any other celestial reference. The anomaly only appears significant because of our particular frame of reference and the narrative we have constructed after the fact. He extended this reasoning further, highlighting that it would also be intriguing if the trajectory pointed toward a known star, the galactic center, the galactic anticenter, the galactic poles, or even the large Magellanic Cloud. From this perspective, the apparent uniqueness of the trajectory was as much a product of selective attention as of physical reality. Professor Wynn then shifted to another dimension of the problem: planetary encounters. He noted that while 3I/Atlas passed close to some planets, it did not make a close approach to Earth. This selective proximity has been cited as anomalous, but he reminded me that it would have been just as notable if the object had passed close to a different subset of planets, only approached Earth, or avoided all planetary interactions entirely. The broader implication was clear. Our perception of anomaly is strongly conditioned by our expectations and the sequence in which we analyze the events. These observations are essential, but without a framework of predictive hypotheses, they cannot be meaningfully quantified. This is a fundamental lesson in the philosophy of science. Noticing unexpected behavior is necessary but insufficient for establishing causal or explanatory power. Without prior predictions, any anomaly can be retrofitted into a compelling story, but the story may have no predictive validity. He reinforced this argument with a discussion of technological hypotheses. He asked whether anyone had predicted in advance that a close approach to a planet's Hill radius might indicate artificial origin, or that the nickel-to-iron ratio in the object's composition would be unusual, or that outgassing jets would emerge in particularly specific directions. These are the kinds of observations that are undeniably intriguing, yet they were only interpreted as anomalous after the fact. The point he was making is subtle but important. To advance a hypothesis scientifically, we must formulate predictions that can be tested and potentially falsified before the observations are made. Without this, any set of anomalies can be spun into a post hoc narrative, but the scientific rigor is missing. He mentioned a specific case of a predicted maneuver near perihelion, raising the question of whether this could be evaluated objectively. This challenge emphasizes the necessity of moving from descriptive anomaly cataloging to predictive modeling, especially if we entertain hypotheses as extraordinary as technological origin. He then broadened the discussion to the philosophy of anomaly itself. By definition, an anomaly is unexpected. It is an outlier, a deviation from the established or predicted norm. He likened the process of discovery to the historical unfolding of quantum mechanics. The anomalies that classical physics could not explain ultimately led to revolutionary insights. Even then, Einstein famously resisted the concept of spooky action at a distance, showing that even when anomalies catalyze new paradigms, the path to understanding is fraught with skepticism and philosophical debate. This historical perspective reinforced his critique. we cannot assume that our current imagination or theoretical frameworks are sufficient to anticipate all anomalies in advance. In astrophysics, as in other sciences, unforeseen discoveries are often the most consequential. When he began his career 38 years ago, the possibility of hot Jupiters, giant planets in close orbits around their stars, was not a topic of prediction or expectation. These objects were discovered through observation, not theoretical foreknowledge, highlighting the limits of our predictive capacity. This insight underscores the tension between celebrating anomalies as surprising and seeking predictive rigor as a hallmark of scientific validity. Returning to 3I/Atlas, Professor Wynne addressed specific anomalies I had noted. He emphasized that the unusual presence of nickel without accompanying iron in the object's composition is highly significant. He explained that this chemical signature corresponds to the carbonyl pathway used in industrial production of nickel alloys. In natural celestial bodies, this ratio is virtually unseen, making it an anomaly of considerable interest. In this sense, he argued, the object bears a signature analogous to artificial illumination on the night side of an exoplanet, a clear indicator of technological processes. The implication here is profound. While the anomaly may not have been predicted, its presence strongly suggests processes that differ from natural astrophysical expectations. Yet, he carefully balanced this by reminding me that the mere identification of anomalies, no matter how striking, does not automatically validate extraordinary hypotheses. It is the combination of anomaly detection, careful measurement, and the eventual construction of testable predictions that constitutes rigorous scientific methodology. Perhaps the most memorable part of his email was the analogy to detective work. Professor Wynne likened the process of interpreting 3I/Atlas to arriving at the scene of a crime. He argued that my methodology, if taken literally, would have detectives ignore unusual facts simply because they were not predicted before the investigation began. This, he contended, would be absurd. Real detectives, including iconic fictional figures like Sherlock Holmes, understand that the unexpected or anomalous features at a scene are precisely the clues that lead to solving the case. The anomalies themselves, regardless of whether they were anticipated, are vital pieces of evidence. This analogy crystallized the tension in scientific reasoning. While prediction is a cornerstone of rigorous science, the identification of surprising, unprecedented observations is often the gateway to discovery. The challenge, then, is to integrate both approaches, honor the anomalies without being blinded by post hoc rationalizations, while striving to develop predictive frameworks that can be tested and refined over time. The philosophical nuance of his argument resonated strongly with me. He was not dismissing the anomalies I had cataloged. On the contrary, he acknowledged their potential significance, particularly the technological hints embedded in chemical composition and trajectory patterns. His critique was methodological and epistemological. Extraordinary interpretations require extraordinary standards of evidence, and without predictive modeling, the low probabilities we assign to anomalies are epistemically fragile. In other words, we can observe something remarkable, but claiming it is unlikely or indicative of a particular cause without prior prediction risks the circularity of post hoc reasoning. This is a subtle but essential distinction, particularly in the context of interstellar objects where the sample size is effectively one. Every observation carries immense weight, but our confidence must be tempered by the recognition of our own cognitive biases and the limits of retrospective analysis. Reading his email, I also recognized the deeper encouragement embedded in his words. He implicitly invited me to take the next step, to move beyond cataloging anomalies and toward the formulation of testable predictions. Could we hypothesize specific behaviors of 3I/Atlas under the technological origin hypothesis? Could we forecast future jet activity, rotational dynamics, or interactions with solar radiation in a way that could be empirically verified? These are the kinds of predictions that could elevate the discussion from descriptive speculation to scientific inference. Professor Wynne's perspective was both a challenge and a roadmap. He urged careful, disciplined thinking. Respect the anomalies, consider their significance, but seek predictive power to solidify any extraordinary claims. Finally, his reflections reminded me of the broader context in which all scientific discovery occurs. Breakthroughs are often initiated by anomalies that defy expectation. Yet the path from observation to understanding is rarely straightforward. We must navigate the interplay between surprise and prediction, between what is seen and what is anticipated. The case of 3I/Atlas exemplifies this tension. Its peculiar trajectory